Now let's move into how we deal with sums of geometric sequences, okay? And this method is named after another famous mathematician, Euclid of Alexandria. He was Greek, and we don't really know that much about his life. He lived, it's said that he lived about 300 BC, so this is way before the time of Gauss. And we just kind of like to name things after people, but I'm sure that people knew about these methods. Euclid is also really famous for being the father of I guess how we teach geometry usually, because he wasn't the one who invented all this stuff. Although he had a lot of, I think he had stuff that he found himself, but he put together the first book that like had all the known rules and postulates and theorems in geometry, and it was very thoroughly laid out, and everything was proven. And it's actually very famous. It's a really good exercise to read that book. In fact, interesting thing, Abraham Lincoln was a lawyer. Obviously, he was our president, but one thing he said was that he read Euclid's Elements regularly, and it really helped keep his mind sharp. So, fun historical fact. Let's go ahead and jump into using this method. You'll notice this is a geometric sequence. In fact, it's actually powers of 3. And we'll talk about how we're going to do this. So I'm going to actually rewrite this so that it's in the powers of 3. Okay. And then, so it looks like we're adding all the things from 3 to the 0 up to 3 to the 5th. And there's something weird we're going to do. We're going to instead of rewriting the sequence itself, I'm not going to have you like think about this one really, because it's not really easy to come up with this. I'm just going to show you. I mean, we're going to actually multiply by whatever the base is, and then subtract that away. So watch what happens here. If I multiply 3 by this sum, then this becomes 3. And then this becomes 3 squared, right? And then, remember, everything multiplied by another 3. So all these are going to jump up by a power of 3. So what we're going to do, though, is we're going to actually line them up, because technically this becomes 3 and this becomes 3 squared. But we're going to line them up so that when we subtract them, they're like terms. So this changes to 3 to the 1 plus 3 to the 2 plus 3 to the 3 plus 3 to the 4 plus 3 to the 5. But then it extends it up to 3 to the 6th. And then we're going to go ahead and subtract that off. Okay? So maybe I'll use a different color here. And subtract this. Well, what do we get? What do you notice? If I subtract everything here, 1 minus 0, it just leaves me with 1 here. And then this and this all the way up to here cancel out, and we're left with, I'm just going to skip all that extra space, and we're left with just a 3 to the 6th there, right? And s minus 3s leaves me with negative 2s. Therefore, our sum itself is 1 plus 3 to the 6th over negative 2. I just realized I made a small mistake here, actually. Slight mistake. When I subtract this, that's why I tell you guys, actually, it's really important. I usually use parentheses here. So actually, me making a mistake is probably a good thing to show you guys. This should be a minus 3 to the 6th, and that should be a minus 3 to the 6th, actually. Okay, so that'll be the final result there. And that's actually really interesting, because that actually makes the sum be really condensed. Now, this might seem weird, because like, all the negatives, if you really wanted to, you could realize that you could pull a negative out front and or put this negative up in the top, because technically it's a negative 1. So it can be written as 3 to the 6th minus 1 over positive 2. Okay, so whatever 3 to the 6th is, if I subtract 1 and then afterwards divided by 2, it turns out I get that. And that's going to be very interesting, actually. Let's look at these next ones. Now that we've done this one, now I'll say you can pause and try these two on your own. Okay, so go ahead and pause right now, and then we'll do them together. Same deal. We're going to call this guy S, and then we're going to subtract off a whole bunch of stuff, and then go from there. Well, remember I said you're going to subtract off a multiple of S, and that should be whatever the base is, because that's how this kind of all works out. So we're going to subtract 2S, and 2S is equal to, well, 2 plus 2 squared, right? I'm just shifting this one entirely to the right, meaning everything's exponent jumping up by 1. Plus 2 to the 3, plus 2 to the 12th, and then there's going to be a last one, 2 to the 13th there. So now again, when I do the subtraction here, S minus 2S gives me negative 1S technically. And all these cancel out, and then again we're left with a 1, that's interesting. And when I subtract off the 2 to the 13th, I'm not going to make the same mistake again I made last time, then I get that. And therefore my S is equal to 1 minus 2 to the 13th over negative 1. Now, real quick, I know that it may seem like we don't need to do the negative 1, or we could just multiply both sides by negative 1, right? And then that'll just flip this around. Technically speaking, it is true. Like really, if I actually simplify this more, it just flips around the 2 to the 13th and the 1 up here, and actually that's my final answer. But we're always looking out for patterns. This negative 2, I actually want you to think about something, came from 1 minus 3. And this should be something that like has a light bulb in your head, because this negative and this negative 1 came from 1 minus 2, right? So now if you look at that and that, hopefully you start to see some patterns happening here, and we can kind of generalize this a little bit. Okay? Let's look at number 3. And again, if you now have a little bit better idea or you didn't know how to do it, you can pause again and work through this one. But you notice that we didn't start with just 1 anymore, but that's okay. It's actually still going to work the same way. And again, we'll just call this S, and we're going to subtract off, well, our base is 5, so it's going to be 5S. So let's go ahead and subtract that off here, and we're going to have to go all the way up to 5 to the 9th. And this gives me 5 to the 4th. Remember, when I multiply this whole original sequence by 5, this becomes 5 to the 4th, this becomes 5 to the 5th, etc. And 5 to the 7th, 8th, and then finally 5 to the 9th. And again, hopefully we're seeing some patterns here. And again, we get S minus 5S is negative 4S equals, now in this case our first term isn't 1, but we still take our first term, and that's the first thing here, 5 to the 3rd. And then when I do nothing minus 5 to the 9ths, it's still minus 5 to the 9ths, if that makes sense to you, right? And then in the end, what we have here is that S equals 5 to the 3rd minus 5 to the 9ths over negative 4, right? But again, I'll remind you, this is, the negative 4 came from 1 minus 5, right? So hopefully at this point we can actually see, let's use orange here, our final sum for each of these things, if we kind of leave it with that pattern, lets us see what we can do. Try to think about that for yourself. If I start out with this, instead of actually doing the whole entire process, you can take your first term minus your last term over 1 minus whatever the base is, right? First term minus last term. Excuse me, I made one mistake. It's the first term minus the term after the last term, actually. So, right, my last term in original was 5 to the 8th, so I actually have to take 5 to the 3rd minus 5 to the 9th over 1 minus 5. And again, first term minus 1 more than the last term over 1 minus the base, 1 minus 3. And same here, first term minus 2 to the 13th, right? The next one over 1 minus 2. And that turns out to be a really cool pattern. In fact, we can generalize this with algebra, and it turns out to go back to a polynomial multiplication pattern that we've talked about before. So let's take a look at that real quick as an example and then do a few more things. Geometric sequence in base x now, right? So it's a generalized base, it's not like a specific number. And we can repeat the process we've been doing and start anywhere we want along the sequence. But for now, let's just look at, we'll start with 1 and add x and then x squared and all the way up to, let's say, x to the 10th. We might generalize it even more in a minute. Find a formula for that that's a little shorter, I guess. And this is another one that's great. You can go ahead and pause yourself and then redo it to get even more practice here. But let's go ahead and work through this ourselves. And same deal. Well, here's the thing. If we want to try to use that pattern we talked about before, let's see if we can remember. On the top, it was always 1 minus x to the next term from our maximum one, in this case, x to the 11th, over 1 minus x, wasn't it? Now here's the crazy thing. If it's true that this is 1 minus x to the 11th over 1 minus x, I want us to remember something. I'm going to erase this. That this is like a division relationship. If I multiply the denominator to the other side, it means that 1 minus x times 1 plus x squared plus x cubed, etc., all the way to the 10th. So 1 minus x times the whole thing should give me 1 minus x to the 11th. Now, this is cool because it turns out that Euclid's method is actually just kind of a tricky way to do distribution of the algebra. If you remember multiplying two polynomials together, or expressions in general, you'll notice that we want to, remember we do each with each, so if we do the 1 times all that stuff, minus the x times all that stuff. Do you agree? 1 times 1 plus x squared minus x times right? Do you agree? If I distribute this 1 in there to everything, and then this x into everything, then I just stacked them up just because. But this looks like Euclid's method, because watch. I didn't use the s here to represent the sum, but if you notice here, this actually, when you multiply this x into everything, it actually makes everything push forward, and this actually turns into x and x squared and x to the third. This becomes x squared, x to the third. So when I distribute that x, it actually makes this whole thing go up to x to the 11th. And I'll just get rid of that x because, oh, and I have to get rid of this 1, don't I? So now it really turns out to be this. And just like we did in our examples, all these cancel out. And what we're left with here is this 1 minus 0 is 1, and then minus x to the 11th. So again, what we did was we distributed this and multiplied it, and we ended up with 1 minus x to the 11th, which is exactly what we saw, or what we expected. Okay, so this lets us generalize even further. Okay, this is an important thing here. And we often use r instead of x, because remember we talked about a common ratio for geometric sequences. If I actually wanted to add 1 plus r squared all the way up to r, let's say to the power of n, I think we've kind of gotten an idea for how this will work. Now we could prove it by physically going through Euclid's method, and that's a great exercise, but we've thought about this and how it works. Do you agree that this is 1 minus r? Well, what's the next term above r to the n? It's r to the n plus 1, right? Over 1 minus r. And there's a really helpful formula for the sum of the terms in a geometric sequence. And there's everything you need to know about Euclid's method. There's one more really cool thing I want to show you though about some certain kind of sums with special geometric sequences we'll look at here, and then that'll be everything. Okay, so here's the last example, and this is a really awesome one. Now, I want you to think about something. If we just had a forever sum for most of the geometric sequences we've seen, like powers of 3, let's say, well, that just gets infinitely large, right? But watch what happens here, or think about with me what happens here. Try to recognize this is a geometric sequence, right? Look for that pattern. This is technically 1/4 plus 1/4 squared plus 1/4 cubed plus etc., right? So the next one would be 1/4 to the 4th and that business. Well, think about it with me. 1/4 is, you know, it's relatively not a very large number, but I mean, it's a fairly large fraction, I guess, because a 16th is much smaller and a 64th is much smaller. And in fact, every single one past that gets like really close to 0. It doesn't really seem like, even if you add up the infinity of the terms, it doesn't seem like it's getting very big very quickly, right? And it turns out actually that is very right, and there's a really cool visual way of looking at this. And there's so many visual ways of looking at how we add up sequences and stuff. Actually, it's really cool. So let's just draw a square here, and I split it into fourths because this is based on our common ratio, right? Our factor, our base of 1/4, yeah. Well, if this whole thing represents 1 unit, let's say, so let's just say this is 1 on all sides of that square, how much of it is 1/4? We'll shade it in. It's just one of those pieces, right? So this here represents 1/4, and I'll do my best here to, it'll help us with later on in a minute to visualize this if we actually have it all shaded in nicely, okay? Well, how can we, that was the first term. How can we represent the next term as 1/16? I actually like to think of it instead as 1/4 squared, like a fourth of a fourth. And I'm going to use this guy up here because if that's itself 1/4, if I split it into fourths, then don't you agree that one of those is a fourth of a fourth? So this here actually represents my 1/16, or my 1/4 squared. And let's repeat that process. We're going to keep going up to the right, but then this here is 1/64, and then we're going to shade the bottom left one and then move up and right again. Now I'm not going to write in all the fractions anymore because it's getting kind of small, but I can split this a little bit more and then continue to shade those. This is a very famous visual proof, actually. Okay, so I can't really go much further than that because of my physical limitations, of course, but I want you to look really carefully here at this diagram. Really, really carefully. Let me ask you this. The total amount of these squares that are shaded, if we did let this process go to infinity, whatever that means, we call this a limit actually in math. We'll talk about that later on, but this infinite sum, as you keep adding the next term and the next term, kind of reaches a plateau or a limit actually. And I want you to think, what fraction of the whole square is actually being taken up by only the shaded squares? I want you to notice something. This big one has 2 other matches, and then this one has 2 other matches, right? If you notice, this whole string takes up exactly 1/3 of the entire square. And notice, that what that means is if we actually added this up forever, it ends up being equal to exactly 1/3. And that's actually true. It's completely proven at this point. This is more or less considered a proof actually, because there's not really a way to refute it. You can imagine that it goes forever that way. And obviously every piece has 2 other matches, right? So this takes up 1/3 of that space, and this takes up 1/3 of all that space. So overall, it actually turns out that if we add forever the powers of 1/4, starting with 1/4, it's equal to 1/3. Isn't that crazy? We can do a similar thing actually for, let me think. Yeah, we can do a similar thing for thirds, I believe. Now I can't really as easily draw thirds perfectly in a square, but let's just use a square again. If I do powers of 1/3 plus 1/3 squared, so that's 1/9, plus a 27th, which is 1/3 cubed, and again, just letting that go forever. Let's split this middle one into thirds and then shade in one of those thirds, okay? And then let's go ahead and actually repeat, and this seems weird, but it actually works. And we're going to draw it that way. There's a third of the next level, right? So this is a third, that's a 9th, this is 1/27 of the whole thing. And then we'll go to the next power, which would be 1/81. I'll shade the bottom of that. And then we'll do this, and shade that, and split again. And I want you to see something here. About what fraction of the whole entire square is being taken up, let's remember this is still a 1 by 1 square, is being taken up by all these powers of a third. Look, it's exactly a mirror image. It's equal to 1/2. Maybe at this point you actually have something in mind for a pattern happening here. All the powers of 1/4 added up to 1/3. All the powers of a third added up to 1/2. I wonder if whatever that is actually is true. For now, we're going to leave it at that. Okay? So again, happy math, and we'll see you next time.